Good morning, everyone. Welcome to day 4. It actually gives me a great pleasure to introduce David Forsyth this morning. So he was actually born here in Cape Town, if I'm not mistaken, and then he he started later at Witwatersrand University in the north, and then moved to Oxford to university to complete his doctorate there. Currently, he's a professor at the University of Illinois, and he has published many papers and books, and I guess that book, Computer Vision, A Modern Approach, is probably his most well-known book. I could, of course, go on and say more things about what he's doing and also his achievements, but I guess you can also Google and maybe we'll also hear as he speaks. I guess he's also a person who would do some diving, since we met yesterday informally here in the lift as he got back from it. Now, one little thing I want to add, about 10 years ago, I was actually in the audience of a place where you were the keynote speaker. And it is one of the talks that I still remember as being both insightful and entertaining. So for that reason, I'm putting now a lot of pressure. I'm really looking forward to this one. Welcome and enjoy.
The general idea is computer vision methods for autonomous vehicles, but I'm going to try and summarize the ideas and applications of computer vision. You want to understand it's a gigantic field, so things are going to be a bit compressed. I'm not aiming for being at the absolute state of the art. I'm more aiming to line out the ideas and how they interact with each other, and the big ones and what they do. First time round, this talk will do sensors and geometry and control. And then the next one will talk about classification and detection and a little bit of regression. And then in the final one, I'll show you sort of more recent applications with respect to weather and lighting and that kind of thing. So today we'll do an intro. I'll show you the big tools, and then we'll talk about sensors and localization. Just to introduce myself, and Illinois is far away and all that jazz. We have a large vision group at the University of Illinois. Vision is a very, very big deal in the States. I'm kind of the famous old guy. My colleague Derek Hoyam has a really neat startup and a bunch of best paper awards. My colleague Lana Lazebnik has a whole bunch of prizes. My colleague Alex Schwing does as well, and he does a bunch of stuff on learning and segmentation. And then my more junior colleagues are focused very much on movement. Saurabh Gupta on visual sensing, Lina Gui on human movement, Shenlong Wang directly on autonomous vehicles, and Yuzhong Wang on detecting and classification with very little data. So it's a very broad group. Now, we have a bunch of books. There will be a new computer vision book, unless it kills me, somewhere about next year, which will be called The New Computer Vision, and I'll release the website probably this afternoon or tomorrow, but I'll give you a URL for a website that has the slides of these talks, associated notes, associated references, and a rough draft of this, which covers some of the registration stuff. We got a lot of well-known ex-students, we got a lot of startups, and so it's all humming along. The other thing that's kind of fun, it's one of the things that justifies my talking about autonomous vehicles, is we have an autonomous vehicles class, and as far as I know, it's the only one in the world with an actual vehicle. So when you do your class project, this is one of the class projects where you've got to brake the vehicle when a pedestrian steps in front of the vehicle. There's a degree of that. There's a degree of commitment required that is not quite the same as in many other class projects. If it doesn't work, you're going to get squashed. Right, there is a safety driver and the like, but it's the real thing. And that's tremendous fun. We have a lot of trouble with the university's insurers and stuff, but it's a great way to do classes. Now, one of the things you want to know about computer vision and the state of this topic is it's one of the dominant topics in science today by conventional metrics. Right? If you look at Google citation metrics, CVPR, the main computer vision conference, is up there with Science, Nature, The Lancet, Cell, and the New England Journal of Medicine. It's one of the top 10 venues in science. This is a very, very big discipline. If you look at metrics on computer science conferences, now scientific metrics are at best weird and mostly nonsense, but it's fun nonetheless because it annoys people who don't do vision. The top computer science conference is CVPR. Then NeurIPS, something to do with machine learning, never been sure. Then the ICCV, then the ECCV, and then AAAI. And this is kind of consistent. Vision is just a very big deal right now. Why? Well, there's sort of two things that are very important. One is we know that for biological systems, vision is fantastically important. Pretty much any animal that experiences light has a vision system. If you get stuck in a cave and go through a couple of generations, you lose it because it's extremely expensive energetically. Now, one of the things that's kind of fun is vision isn't canonical. So we think of vision as telling us exactly what the world we see around us is like. And that's not true. It doesn't do that. You'll see here, this is the penguin reserve, just a little up there towards Royales. And you'll see in the photo there's a penguin standing by one of those little concrete tunnels that they use. And then next to it is some weird thing. And that weird thing is a stake with a bunch of bits of plastic that are white on one side and black on the other side, and they flap in the wind. Now, what is that all about? The answer is predatory birds that steal penguin chicks do not like to go near large concentrations of penguins because they're going to get clobbered. They want to go to an isolated penguin. If you stick a bunch of those things, predatory birds, their vision system says that is a moving penguin, and they keep away. So what's important over here is A, they see, and B, their vision system very often lies to them, and you can fool them as a result. Okay, now what the primary recipe that has made vision successful looks roughly like this. You get a data set, you make some features, you build a classifier, you submit a paper, and you kind of loop depending on whether it got accepted or not. It turns out this is old-fashioned and completely wrong. We know that the correct recipe is this, right? It's an extremely powerful, very valuable, very useful recipe. Onwards and upwards, right? But there are some problems here. One is this recipe is fantastically expensive. It's expensive because you can only make it work if you can collect data sets. The competitors who are collecting data sets are organizations that have more money than is even remotely reasonable, and that means it's tough for universities. It's actually quite a fragile recipe. You can make it do wonderful things, but there are all sorts of places where it stops working, and it's kind of routine. So that poses problems for academics in vision, and essentially you could do one of two things. One is you could kind of join a crew, go hang out with Meta or some other organization. Some people like it, others find it boring, or you can just sort of do stuff that industry can't or won't do, which is mostly right now low or no data learning. Okay, so I'm going to start talking about the big tools. So I think there are three really big ideas in vision. One is geometry, the other is discrimination, and the third is regression. And we'll see each of them. So there are two sort of questions in geometry and vision. You can think about pretty much everything in these terms. One is registration. I have a little model on the one side, I have observations on the other side, and I want to figure out what transformation takes the observations to the model. So for example, the model could be a CAD model of some 3D object. The observations could be a picture, and I've got to figure out how the object was rotated and translated to form the picture in the camera. There are a bunch of cases of registration. And the other one is multiple view geometry. I have 2 pictures or 3 pictures or more pictures. What do I know about the world based on those 2, 3, or more pictures? So registration is a very general recipe. We know how to do registration for 2D models to 2D images or 2D observations, 3D models to 3D observations, 3D models to 2D observations, etc. We know how to do it when things are represented as points, as lines, as various geometric primitives, etc. It keeps coming back and back. So there's been a literature on this running through 50 years now. Keeps coming back and back because it's extremely useful. I'll sketch out some registration procedures as we proceed. Multiple view geometry, again, what can we impute from two or more views? And the answer is, of course, lots. We can impute how the camera moved or the transformation between the two cameras. We can impute how things are moving in the image, and we can impute the 3D structure of the world. Very, very powerful ideas. So the next big tool is discrimination. I'm going to use some procedure to attach a label to an image, some images, video, range data, LiDAR data, etc., etc. As we'll see later on, label can be fairly loosely interpreted. The procedure could be learned, it could be hand-tuned, or it could be the result of physics. But the basic thing is, an image goes in, or video goes in, and a label comes out. Image goes in, cat. Image goes in, fish. Now, discrimination is interesting. Mostly, it manifests as image classification. Image goes in, usually there's a bunch of sort of neural stuff. I'll talk about some details in the next talk. Then out comes a label that sort of says cat, dog, whatever, car. What I'm going to do is adjust that neural stuff so that it accurately classifies unseen data. It's not that interesting to be good at classifying data whose labels you know, because you already know the labels. So I have to adjust the classifier so it classifies training data well and generalizes. And that's the job of regularization terms, etc. And then in evaluation, I'm going to use held out data to check. There are two strands here. One is classification. There is a cat in the image. The other is detection. The cat in the image is over here. Put a little box around the cat or a circle around the cat or something of that sort. And of course, in detection, you have to worry about how you specify where. Is it a box? Is it a circle? Is it a mask? You have to worry about the relationship between what it is and where it is. Turns out there are two threads in detectors. We'll talk about that a little bit later on, where that relationship is handled in very different ways. And then it turns out that evaluation can be surprisingly fiddly. Let's talk about the practical problems. So it should be pretty obvious that a fish classifier over here is going to be in good shape. Are there fish in the image? Yes. They're the sort of big ones in the middle. It gets more interesting when things are hard to find. So there is a clip for there, but it'll take you a moment to spot it. It's the little green guy. You can see the little white strand over there. Do we have a pointer or a ruler or a long thing? Maybe there's a little piece of aluminium. Let's use that. Should have thought of this. Here we go. It'll do the work. There we go. It's over there. You can see the little white strand. You can see its eye and its body. So the actual process of determining whether there is a fish, it's a little tricky. Fish spotting is basically fairly straightforward. Anybody spot the octopus? Right? That's a bit more interesting. So this is yesterday's octopus. Here's a slightly different view. If you pay attention, you can see its eye, which tells you where the rest of it is. You can see the eye sort of over there, and then the rest of it over there. It's cuddled up under the algae, and it'll, in about 2 photographs' time, it'll stick a tentacle out and take a shell from the dive master. So it can be hard. Things can be very hard to find. The other problem you could have is you may not actually know the right label. So most people will realize that there is something interesting in the picture, simply from the framing, semantics, and the iconography of the picture. The question is, what label do you attach to it? A very small fraction of the audience might say, oh, well, that's obviously a flame nudibranch, because you've been there before and you know the label. Many other people will say, well, it's some piece of sea life, because it's pretty obvious it's marine. It's fairly obvious that that's the interesting thing. So the question of what you say about unfamiliar things is hard. And it's hard in this discrimination framework. Here's another example of unfamiliar things. Are those hydroids? Are they anemones? Are they coral animals? They're submarine because all of my photographs are submarine, but precisely what is going on. It turns out they're strawberry anemones. So there are real difficulties to be dealt with, and we'll talk about some of them in the second talk. So what I want to do now is talk about what you could do if you could exploit registration and classification. What I'm going to do is the following. We have a car, it's got a camera. I'm going to build classifiers that sit on the pictures and will report a variety of kinds of information. How far is it to the next intersection? What is it like at this intersection? Are there bike lanes, etc., etc., etc.? So, for example, you can see there, ooh, that's a little bit dark. Oh, well, you can see there, it says stop on the ground, and the prediction is about 18 meters to the intersection. That's actually correct. So the first question, how do we do this? And there's rather a neat paper which will be on the website, and I'll have a pointer to it. This is about 5 years ago, where what they did was they took OpenStreetMaps. Now, the thing about OpenStreetMaps is it's basically a very good, very accurate set of maps that are open source, so you don't run into copyright and trademark problems. Now what I'm going to do is I'm going to go to, Google Street View. And Google Street View gives me piles and piles of images, and I know where that image was taken. So I now take those images, I know their orientation, I figure out where it is in OpenStreetMaps, then I go to OpenStreetMaps, and I look at how far away am I from the intersection, which is just like a computation on the data set. And I look at, is there a stop sign here? Because OpenStreetMaps tells me. I look at it, am I oriented this way, et cetera, et cetera. And I can now label. I'm basically going to match those panoramas to roads. I can get annotations of intersection, of drivable heading. If I go this way, is it drivable? If I go that way, is it drivable? If I go that way, is it drivable? Heading angle, bike lane, speed limits, wrong way, etc. And then I get classifiers. And these classifiers are going to say things like, let's see, that's viable. These classifiers are going to predict fairly accurately how far I am from an intersection. So in the first case, the prediction is about 0.1 meters, and true is 1.9 meters. A couple of meters, that's pretty good. Prediction 18.5, true 19.2, pretty good. Prediction 22.9, true 22.4, pretty good. So I know how far away I am from intersections. I can figure out intersection topology. What my classifier is now going to do is, instead of reporting a label in the form of distance in meters, it's going to report a label in a form of heat map, which says the yellow stuff basically tells me I can drive, the blue stuff basically tells me I can't drive. So if you look at the top row, the little blue is the location of the picture, or the location where pictures are taken, and then there is a circle, and the blue stuff you can't drive, the yellow stuff you can. So the classifier is basically telling me I can go forward, I can go backward, I can go left, and I can go right on the top one, and the second one is telling me it's a T-junction. I can tell if, for a particular view, what is in front of me is drivable. Right? Again, it's a straightforward discrimination problem. You classify. The first case, you really shouldn't go forwards. The next case, you can go forwards. The last case, you really can go forwards. I can tell whether I'm heading along the direction of the road. Right? So if I see the first image, I'm predicting that I'm basically about 50 degrees off the direction of the road. The second one, I'm predicting that I'm about 18 degrees off the direction of the road. The third one, I'm predicting I'm about 30 degrees the other way off the direction. So I can tell, am I going straight down the road or zigzagging? And, are there bike lanes, can be told accurately, etc. Speed, what is the speed limit? Very accurately, 26 for 30, 30 for 50, 54 for 50. So this is all basically straightforward classification. Is this a one-way? Am I going the wrong way down a one-way or on the wrong lane? How many lanes are there? Okay, So at this point, I can tell from an image, using classification procedures that we haven't yet discussed, that I'm pointing in the right direction, I'm going the right way, I'm facing an intersection, what the available turns are, and the obvious question is, can I build a reliable controller? And the only way to think about this question is, if I could, then it would be driving around in the streets right now. Right? This is about a 7-year-old paper. It's pretty obvious that there must be some kind of snake in the grass here. And the answer is, the answer has to be, you can't because it doesn't work. And the only question now is why? And the reason it doesn't work is interesting. Okay. Questions at this point? Everybody with me in the sort of big picture? It's clear from a picture, I can tell all sorts of good stuff about where I need to go. I can tell where I am on a map, and really, you're still not getting into autonomous cars. There is not a drivable taxi you can call up. There are a couple in the South Bay, but they're a bit limited. So to think about this, we have to think just a little bit about imitation learning. I'm going to introduce very briefly, just to set up some technology, the Markov decision process. So I have an agent. It's moving in an environment. And the clock ticks. So at every tick of the clock, the agent chooses an action. This is kind of a generic control. Then something happens in the environment, and the agent gets a reward, and its state changes. So the agent could be a car. It says, I'm going to go forward by a meter. The environment says, well, actually, there's a bus in the way, so your reward is minus 1,000, and your state is you're all mangled. Or I'm a car. I'm going to go forward a meter. That was road. Your reward is 0 because nothing happened, and your state is you're a meter further along the road. It's a very, very general model of control and in which you can learn. And you can decorate this model with notation. So there are states, there are actions, and then there is a transition function. So if I am in a state and I take an action, then in some stochastic way, the state changes. So I'm over here, I go forward by a meter, and some random stuff happens and it tells me where I am. So I'm over here, I give instructions to go forward by a meter. The road is wet, I actually go forward by 5 meters because for probabilistic reasons, and that's my new state. And there's a stochastic reward function. If I choose this action in this state, I get this reward with some probability. And then there's a horizon. And then, of course, what I'd like to be able to do is act in a way so that I get the best rewards. This gives me a framework for thinking about learning and control. What I want to do is basically build an agent that behaves well. Now, I could do it a bunch of different ways. So if I have a known environment and I have known rewards, so I know the state transition function and I know the rewards, then what I'm doing is I'm essentially solving a Markov decision process. I basically do math, and that tells me what my policy is. And a policy is, if you're in this state, take this action. If I have an unknown environment and unknown rewards, then what I have to do is reinforcement learning. I have to figure out my policy, and I've got to figure out my policy by doing stuff and seeing what happens. Rather loosely, I hope that if I've got the right tuning process and the right training data and a bunch of other stuff, eventually it behaves. Now, this is obviously not practical in the form I've described for building autonomous vehicles. It essentially says, go out and drive it, and every time you bust it, change your controller until eventually it stops happening, leaving behind you a trail of carnage. So you don't want to do that. How would you do that? In practice, you'd get a simulator. How do you know that your simulator matches the real world? Well, you don't, and you've got to worry about it. Mostly, it's not a particularly good idea right now because it's not practical. It's a great way to write papers. The data demands are completely unreasonable, and as reliable technologies go, it's not quite there yet. It'll come. But now imagine I have an unknown environment, I have unknown rewards, but I can see an expert. So we've got lots of drivers out there. I'm going to sit a little computer next to the driver and I'm going to collect data. So you could see I put a real driver in the car with my camera on it. I compute the output of the discriminators, and I record that, and I keep track of what the actual driver did. And I can do two things. One is, I can choose a policy that says, I'm going to do what the expert does. And of course, in a new situation, I'm going to make my best guess at what the expert does, and I'll do that. And then the second thing I could do is, I could figure out the expert's reward function, and I could maximize that reward function by choice of policy. The first is known as imitation learning, and the second is known as inverse reinforcement learning. Now, you could take what I described and actually build an imitation learner. And the way you would do it is this. You've got the car, it's got a camera on the front, you know it'll tell you whether there are stop signs, anything else. You've got a description of the image. You stick that into a discriminator, and the job of the discriminator is to produce the same action that the driver produced for the same pictures that the driver sees. The driver drives the car around, the pictures come in, you get your representation, you try to build a classifier that predicts the same thing that the driver does. That's imitation learning. It comes with a problem. And the problem is the following. It's a cumulative error problem that is sort of obvious once you've seen it, but it's not so obvious until you've seen it. Imagine I do this, and I move along the path. My controller moves the car along the path, but it makes a small error. Now, what it's going to see is a picture that the driver never sees. And the reason it's going to see is a picture that the driver never sees is the driver doesn't make small errors. You know, you're going down the freeway, you make a small error, and your car is at 10 degrees to the direction of the freeway. You don't do that. But a classifier might. Once it's done that, it's seeing a picture that it's of a kind that it's never seen before. It's more likely to make an error. So now what's going to happen is it's going to predict some kind of control input that is even worse. And then it will see a picture that is even more out of distribution. And then it will predict a control input that is even worse, and catastrophe results. Right? That is a standard failure of imitation learning, and it's an important mechanism. Questions at this point? Okay. See where we're on timeline. We're good. Sometimes known as data distribution mismatch. I just stuck that slide in because we get the crash at the end. Okay. Now, there are two ways you can fix that, and neither of them are completely satisfactory for our purpose. One way you can fix it is you can collect more pictures. Imagine I'm concerned that my car might drift slightly off in orientation. Then what I could do is collect pictures that look slightly to the left and slightly to the right, and then correct the control from the driver to take into account that angle. And now what I know how to do is deal with small drifts. And that works. It's known to work. It's been known to work since the mid-90s, and it was rediscovered in 2016, and it really works quite well. The other thing you can do is known as Dagger, which is worth knowing about. And Dagger is the following. I'm going to train a policy the way I described, and I've got it from a data set. Then what I'll do is I will run that policy, and then I'll ask the human to label, a real human expert to label images with the correct action. Now, fairly obviously, I'm not going to do this with a car driving around in the streets because there'll be chaos. But essentially what happens is the expert sits in the car, you drive it, now you get a policy. Now you drive the car with the policy, and the expert says, no, you can't drive like that, and labels some of those new pictures. You stick those in the data set. You now retrain the classifier to tell you which direction to go in, and then you drive that. Then the expert relabels the pictures, you retrain, and you keep going. Now, there are two basic problems with Dagger, which are important. One is you have to execute an unsafe policy. And the other is you've got to sit down with the expert and say, did I do the right thing? So we can reasonably hope that by producing better representations of the world, we can do better. But you want to see, I've laid out the carcass of a simple autonomous procedure here. You could build something that almost worked like this. Questions at this point? Okay, so let's look at some of the tools. I've laid out simple visual control. I'm now going to sort of start talking about sensors and localization. So the third big idea in vision, before we deal with that, I'll do the third big idea. The third big idea in vision is regression. I stick an image in, and out comes an image. I stick a video in, out comes a video. I stick an image in, out comes a depth map. I stick a point cloud in, out comes a different point cloud. I stick LiDAR in, out comes an image, whatever. And these regression procedures, I make them sound straightforward. There's a great deal of work involved in what goes in the box. But conceptually, they're straightforward. Why? It's useful. The most useful cases, we'll talk about depth maps from single images, ground maps from an aerial image. You overfly something and you want to label vegetation, roads, houses, that sort of thing. Modified image from image. You've got a dark image, you want a bright image. You've got a blurry image, you want a non-blurry image. You've got a low-resolution image, you want a high-resolution image, that sort of thing. Okay, how do you do it? Adjust the regressors so that it accurately predicts the output for unseen input. You basically adjust it so that it predicts well for training data, and it generalizes, and then you evaluate on unseen data. And I'll talk about the mechanics of how you build one in the next talk. Okay. So what I want to do is produce representations that improve control. I want to be better than just an imitation learner. And today what I'm going to do is talk about registration maps, which tells me where am I, and I'm going to think about how have I moved, which gives me odometry and SLAM. But we've got to do some sensor stuff first. So what do we have for sensors? Well, I'm going to talk about the basics of cameras and what they do. So perspective, lenses, extrinsics and intrinsics, and calibration. Here is a model of an abstract camera. I have a little box. It's got a very tiny hole in it at the front, but otherwise it's light tight. At the back is light sensitive stuff. Now, the only light that arrives at that point at the bottom at the back must be the light that came through the hole. If the hole is small enough, right. Oh, we're back. Okay, whatever. If the hole is small enough, it's basically traveling along a straight line. So I'm going to get a focused image at the back. This bright stuff will be bright stuff on the bottom. Dark stuff will be dark stuff at the top. This is an abstract camera model, but it's actually quite a good abstract camera model. You can also build one of these. Used to be a childhood entertainment. You take a matchbox, you make a little hole in the front, you put some film in the back, and you're in business. The reason pinhole cameras are interesting is they give us a decent mathematical model of what cameras do. If you have a 3D point, big X, big Y, big Z, it'll turn into a point on the image plane, F big X over big Z, F big Y over big Z, F. So basically, 3D, X, Y, and Z turn into two useful numbers and a fixed number. And that, of course, is in the camera's coordinate system. Okay, perspective generates a fair number of interesting qualitative effects. So lines project to lines, distant objects are small, parallel lines meet in the images, planes have horizons, planes, images, half planes. There are details in the notes. I'm going to skip doing the details here. Pinholes emit very little light and only work because they're small. If you want more light, you get defocus. So you got to stick a lens in front. Lenses make things brighter because they collect more light. Then they readjust the rays in various ways, often slightly annoying, and then they end up at the back. There are some mild annoying phenomena associated with lenses. There's spherical aberration, so you get a little bit of defocus and you get changes in shape. Colors can change a little bit because of chromatic aberration. There's a certain amount of scattering at the lens surfaces, and there are geometric phenomena. The ones we would care about the most are geometric distortions. So if you look at a neutral grid, on the one side, many lenses will give you a barrel grid or a pincushion grid. And that's just because of distortion in the lens. Okay, so in its own coordinate system, the perspective camera will take big X, big Y, big Z to fx over z, fy over z, f. But we don't usually work in the camera's coordinate system. Really, there's some other coordinate system out there in the world. There's a UVW out there that ends up in the camera. And what we have to do is think about two transformations. We've got a point in 3D, which I've written with 4 coordinates, because I want to use homogeneous coordinates. Look at the notes. We don't need the details, so it doesn't matter all that much. And I'm going to have a transformation mapping the world coordinates to the camera coordinates. That's sometimes known as the extrinsic transformation. Then there will be a standard camera. That's that little CP. Then there will be a transformation mapping the image plane coordinates to pixel coordinates. Why? Because the world coordinates are measured in meters, and the camera coordinates are measured in pixels. We need to know how many pixels there are to a meter, and that's what makes that change. Those are known as intrinsics. So camera intrinsics occur because the coordinate system on the pixel plane of the camera may not be the same as the standard camera coordinate system. So I've got a little u and a little v. The origin of that coordinate system may not be at the center of the camera, and it might be a little bendy, etc. So that gives me a problem, which is camera calibration. What are the intrinsics of the camera? And the answer is, if I make a calibration object and take a picture of it and do a certain amount of math, I can recover the camera intrinsics. So you can know the intrinsics of a camera relatively easily. Okay, so we've dealt with all we really need to know about cameras. I'll talk briefly about LiDAR. LiDAR is essentially straightforward. You fire out some light, you count how long until you see it come back. You then use the speed of the light to tell you how far away the thing that reflected the light was. You've got to do a great deal of work making sure that you count how long between when you fired the light and when you get it back. You've got to count that very accurately. You've got to sweep the little beam of light all around. You've got to do all sorts of other stuff. But basically, it just gives you a distance to a reflector. And it will give you fairly detailed distances to fairly detailed reflectors. So you can see over here, ignore the fog, rain, very bright light. You can see over here LiDAR returns from a LiDAR of a car in a tunnel. And those little colors are actually very large numbers of little points where the reflectors are. So I get basically a detailed point cloud of the world around me. You can use a thing called a gated camera. They're not that popular right now on vehicles, but they're coming, where you illuminate the world, you then wait for a little bit, you turn the camera on for a very brief time, and then you turn it off. And what that means is you see only things that are in a certain range of distances. Because essentially, the camera doesn't see anything until your light hits it. You've set that up in such a way that your light hits it only when it's some distance away, and that means you can see through bushes. So you fire out your light, you wait for long enough that the light has gone through the bush, then you, and come back, and then you open the camera, and all you see is the stuff that's behind the bush. It has all sorts of military applications, as this picture unfortunately implies, but it's being used now for autonomous vehicles as well. And finally, there's straightforward radar, which is basically like LiDAR, but it happens at very much longer wavelengths, which means the antennas are bigger, the spatial resolution is smaller, the antennas are less efficient, and there's more power. As a result, radar tends to be used only for, is there something in front of me? Is there something behind me? Is there something to either side? It's often used for crash avoidance and detection. Okay, so let's talk localization, unless there are questions. Question. Mm-hmm. Yeah. No, okay, so in case others didn't hear the question, should an imitation learned policy, is it a good thing? It must capture the human factor because watching a human expert, right? If I rephrase it, is it a good thing that it captures the human factor because it's watching a human expert? Gee, you could start a fight in almost any bar full of machine learning people with that question, right? The extreme reinforcement learning position is it's insane to follow humans because they're not very good, right? If you really can learn an optimal policy, why would you follow a human because their policy probably isn't optimal? Because that's just not the way we're made, right? That position, to my mind, is a little bit silly because the pragmatics of producing optimal policies with current reinforcement learning machinery are basically insolubly hard, right? Particularly in cases of vehicles. From the perspective of the robotics community, reinforcement learning is largely an amusing thing that learning people do to play Go, right? It's very hard to run a physical object often enough to get data traces. The simulations are unreliable. You really can't get enough data to train current reinforcement learners to be optimal. That means you might have to accept a suboptimal policy, right? Because you can't get an optimal one. If you're going to get a suboptimal policy anyhow, you might as well get the easiest one that you can get, which is usually the one that you can beat out of a human. So I don't want to talk about whether it's a good thing or a bad thing. It's certainly a practical thing, right? It is often much better to imitate humans than it is, or it's often much more practical to imitate humans than it is to be better than them. Right? Which is not anything about whether it's good or bad. It's just a statement of pragmatics. I'm willing to believe, I find it easy to believe that there are policies that are much, much better than human policies. There's very good evidence that properly built freeway drivers, for example, are better than human freeway drivers. They don't get tired and they don't text on their cell phones, a bunch of other, that sort of stuff. But it's not that easy to get an optimal policy without watching an expert. It's entirely a pragmatic matter. Other questions? Sure, please. Okay, I don't do much imitation learning. There are imitation learning demonstrations where people use a single expert and a short demonstration, right? There are imitation learning demonstrations where you use multiple experts, multiple demonstrations. It mostly depends on the task. Again, for pragmatic reasons, it's very desirable to be able to frame the task in such a way that you use very few demonstrations from very few experts. This is one of Dagger's big weaknesses, which is you've got to go back to the expert. What you really, really want to do is watch a person doing something and say, oh, I know how to do that, and just do it right. And there's a great deal of work pushing in that sort of general direction. Cool. Further questions? Other issues? Okay, so we'll go back to localization. I'm just keeping a weather eye on the time. I might compress a little bit. So here is point set registration. I'm going to sketch it very high level, but it's very powerful. So imagine I have a map, and my map is going to consist of LiDAR returns. I will go out and I will collect, imagine I want to make a little autonomous vehicle move around this room. I'll drive around the room a bunch, I'll get a lot of LiDAR returns, I will do stuff, and I will get a LiDAR model of the entire room. Now imagine that vehicle is over here. It collects LiDAR. It's going to get point set measurements. If it can figure out the transformation from the point set measurements that it gets to that map, it knows where it is. Right? So being able to register is obviously very powerful. Now the nice thing about this is, imagine I am over here and I have a set of point set measurements. And I move just a little bit. And I get another set of point set measurements. I can register the second set to the first. and that'll give me some extra points. And then I move again, and I register. And I move again, and I register. And I move again, and I register. And I move all around the room, registering. Then I have a map, because I know where all of the points in the room are with respect to each other. I can keep that map, and whenever I move around, I look at my LiDAR, I register, and I know where I am. Everybody with me on the general picture? So this registration trick is fantastically powerful. So I will leave out filtering because it just gets us involved in complications that we don't have time for. Here is the simplest case. Imagine I have beacons. On the wall at every 5 meters, I've placed a little label, and the label says I am label 1, I am label 2, I am label 3. And my measurement process says label 1 is over there, label 2 is over there, label 3 is over there. And I want to register up to rotation and translation. The way I can do that is I can choose a rotation and translation that minimizes the squared error in the rotation of r of x, the measurement, rx, the observation, plus the translation, minus the beacon position. If I minimize the square error of that, then I should have a good rotation and translation. Now, what is news about this to many people is this can be done in closed form. It's extremely easy. You do a bit of fiddling around with matrices, and R and T fall out. That's in the notes. Do not ever forget the fact that it can be done in closed form, because it's embarrassing to do it with an optimization procedure and then have a referee send back a note saying, yeah, but it was worked out in closed form in the 70s by Horn. Okay, so I can register. The problem with the story that I told is I may be in trouble if I don't know that this measurement corresponds to that beacon. So think about the LiDAR problem. There are a bunch of points out there in my map. I've got a bunch of points. I do not know which of my measured points corresponds to which point on the map. So it's a little bit harder than it used to be. What do I do now? The other problem that I'm going to run into is, and your instincts might have fired here, but it is never a good idea to use a squared error, because a squared error, if the error is large, is gigantic. It dominates, and you get a robustness problem. So we will talk very briefly about both of those. Here is a standard and extremely powerful algorithm. Imagine I do not know which of my measurements corresponds to which of my points. Then what I can do, what is known as iterated closest points. I'm going to say every measurement corresponds to the closest map point. And then I will compute a rotation and translation. And then what I'll do is change the correspondences. I'll now take each of my rotated rotated and translated measurements, now find the closest y, and then I'll go again. And then I'll find the closest, and I'll go again. And I'll keep doing that until nothing changes. And I'll say, now I'm registered. This is an amazingly simple, very, very powerful, very big idea with tons of variants. And the variants usually are, what is closest? There are all sorts of ways of thinking about what is closest and how you find the closest thing efficiently. Clearly, if I've got lots of points, I want to reduce the number of points, otherwise that's going to be expensive. There are tricks for doing that as well. Robustness is now a serious problem. So here is an example of the nastiness of robustness. On the one side, you'll see a bunch of points and a line that has been fitted to the points with just least squares line fitting. Now I added one point. You can see the point I added. Oh, it's got Velcro on one side. That's why it's so hard to pick up. Oh, thank you. Yeah, there we go. Thanks. Easier to pick up. You can see there's a little point down here that I added to the data set, and that one little point has caused the line to swing hideously. Why did it do that? Well, because I'm using least squares error. So the distance between the true line, which has to look something like that, and this point is gigantic. If you square it and add it into the error, it's appalling. So what the thing does is to try and make this distance smaller, and it's willing to accept bigger distances over here and now I'm in a horrible mess. I've got completely the wrong line. That effect is going to occur when I try and register. If I have points that are really far away, their error is going to dominate, and I'm going to get the rotation and the translation wrong. What do I do about that? Let's ignore that. There are several fixes. One is I can throw away pairs of points that are too far apart, which turns out to be actually quite good. The other is I can apply a thing called an M estimator, which weights down big distances and up small distances, and I can build that into the iterated closest points loop. Again, details in the notes. I'm just sort of illustrating variance. Okay, so imagine I do all that stuff. I can robustly register a point set to a point set. This is localization. I can look at the LiDAR, I can register to a map, and I know where I am. How do I make the map? Well, basically, I'm going to register things, but there is one small problem. So in my one small problem, imagine I register A to B, and then I register I register B to A, then I register C to B, then I register D to C. Right? Now, I get the squared errors from this to this smallest, and from this to this smallest, but I'm not actually registering C to A right. And if I do that process of registering B to A, C to B, D to C, I'm going to discover that my collection of things joins up badly down here. Because this is joining that well, this is joining that well, this is joining that well, but the errors in the transformation accumulate. Now, what am I going to do about that? A fairly natural thing to do is to say, well, do this, and then fix these three, take that one out, improve the registration, put it back in, take that one out, improve the registration, put it back in, keep going. Right? Everybody with me on the rough algorithm? That is slow, but it's effective. Okay, there is an alternative. That's slow, but it's effective. Now, what I see is we're at 9:56, and I've done what I thought was about 40 minutes worth of stuff. We're not going to do multiple cameras in great detail. The details are in the slides. The main point that I want to make, so I was going to talk about epipoles, pairs of cameras, and the like, but I want to make a couple of points about them. So we'll skip the detailed geometry, and I'll show you a couple of movies about good stuff that comes from it. Here is two pictures, multiple view geometry. Picture one, picture two. Notice something interesting. I get two measurements over here, I get two measurements over here. There are 3 degrees of freedom. So I've got 4 measurements of 3 degrees of freedom. That means there's something redundant in the measurements. And in fact, if you want to do a great deal of math on your own and you're feeling wildly creative, this is actually all of multiple view geometry. 2 views of a point give 4 measurements of 3 degrees of freedom. That means the correspondence. The point in the left image that corresponds to the point in the right image, the point in image 1 that corresponds to the point in the image 2 is constrained and much harder. This took about 20 years, right? So don't do this at home on your own, or if you do, don't be disappointed if it takes a little bit longer than you think. But if you have enough points and enough pictures, you can recover the position of the points in 3D and how the cameras moved, if it was a video, or the relative location of the cameras, if it was a pair of cameras.